Okay, this is section 1.5, differentiability and continuity. So we've been talking about the derivative for the last couple of sections, and in our minds, I'm hoping that when you think of differentiability, you're thinking the slope. Like differentiability and slopes, they really go hand in hand. So not all functions are differentiable, just like the slope is going to be kind of weird in some places. Not all functions are going to be differentiable at all places on their domain. So functions will not have derivatives at points where they have sharp corners, like open spots, gaps, breaks, or wherever the tangent line is vertical. So I've got a bunch of functions here to walk you through. So this first one in the upper left-hand corner right here, let's get the marker. Right at that point, you'll notice the slope is pretty constant, and then at that point, it changes to be a different point. So if we were to zoom in just on that point right in the middle right there would have two different slopes. So that means it's not differentiable. And the idea is the same on the second one, the top right corner. The slope is perfectly constant until here. And then right here at that same point, the slope is almost becoming a horizontal line. So these two slopes are contradictory. So I would say it's not differentiable. Okay. And yeah, the same thing right here. There's like the slope. If you go from the left side, the slope looks sort of like that. If you go from the right side, the slope looks like it's going to be almost flat again. So since at that point there's contradictory slopes, it's not going to be differentiable right there. And then, I mean, it's even more pronounced in this one right here. There's a giant gap here. So the slope is almost like that from the left, and then it's almost flat from the right, and those points don't even touch. So it wouldn't be differentiable right there. And then up here, if you think about, so actually it's down here, my bad. The tangent line here is vertical. So if we're talking about slopes, the slope here, you go up like a billion, and then you don't go left or right at all. So it's like 0. So this is an undefined slope, like you can't divide by 0. So that tells me that at that point, it's not differentiable because there isn't like a number for that slope. So right there, not differentiable. And I can make the exact same argument here at 1. There's no, the slope is just completely vertical. So the slope is undefined. Therefore, it's not differentiable. So let me know what you think about that, if that makes sense. I kind of feel like after section 1.4, I feel like this is a lot easier because I think section 1.4 is kind of tough. But again, let me know if you have questions because maybe you think differently than me. So the next thing in this section is continuity. So differentiability, that's more about slopes. Continuity is a different thing. Continuity, a function f of x is continuous at x equals a, provided that the following relationship holds. So I'm going to draw a picture of something, just like a weird curve. Okay, the first thing is when we talk about the limit as x goes to a, that means on the x-axis, there's some value a that we're thinking about. And this curve I drew, that's the function f of x. So this relationship right here is kind of saying that the limit as x goes to a, whatever point that is, it actually has to equal what a f of a is. We'll talk more about that. So there's 3 conditions that need to be met. One of them is that f of x must be defined at x equals a. So I couldn't erase right here and put a dot. So I couldn't do something like this where I've got the same curve and then a hole at x equals a. That's not going to work. It has to be defined all the way through like that. No holes or anything. And then the limit as x goes to a must actually exist. So the limit has to exist. And not only does it have to exist, these two things actually have to be equal to each other. So knowing that, let's give this first one a shot. Draw one continuous function, one discontinuous function, one differentiable, and one function that is not differentiable. So we're kind of tying in all the things that we've just talked about. So the continuous function I feel like is pretty easy. A continuous function is just one that doesn't have any breaks or holes, and you can just draw it without ever picking up your pencil. So a line works. So this is the one that's differentiable. Okay, so I need one that's I'm sorry, I said differentiable, but it's continuous. It happens to be differentiable also, but I'm doing the first one, which is continuous. Okay, the second one is discontinuous, so I just need to draw something that I have to pick up my pencil. So I'll draw the same thing, but with like a gap in it. So that one is discontinuous. And then I need one differentiable. And from our earlier work, we know that just like a straight line is differentiable. So I'll draw another straight line. Differentiable. And then I need one function that is not differentiable. So I need the slope to be a little wonky. That's the idea here, is a little wonky. So I'm going to draw like a bloop, like a little corner. So that one is not differentiable right there. I think this, if the more problems you do, the easier this sort of becomes. You see more functions, you get the idea a little bit more. So let's keep trucking along. All right, use the graph below of f of x to answer the following questions. Where is f of x not differentiable? So I'm looking for places where there's breaks or where there's awkward slopes. So I usually start on the left and then I work my way right. So this slope is all smooth here, so I think it's fine. But right here at -3, we have a problem, so I'll list that. And I also want you to assume that this graph continues just kind of like that to the left. So at -3, we know there's a problem, and then at -3, this all seems like a smooth slope until -2, where the slope is negative, like that, going down, and then it seems to be positive right here. Either way, the slope is wonky at -2. So -2 is another problem. And then it's all fine until we have this vertical line here. We talked about how vertical lines are a problem. So -1 is also an issue. And then the slope again seems fine, very smooth, nice and differentiable until 2, where one thing that we talked about is that in order for something to be differentiable, there has to be like no holes or gaps. So at 2, we've got a problem. But then after that, everything seems fine again. And I do want you to assume that it just keeps going like that. Okay, so if like this was a problem you were going to turn in, I would like it if you put x equals -3, -2, -1, and 2. Because if you don't put the x there, maybe you're talking about the y-axis, and that would be confusing. So then the next question is, over which intervals is f of x differentiable? So basically it's everything but those points where it's not. So starting from the left, that's -∞ to -3. And then I'll union that with -3 all the way to 2. Union, that's a -2. -2 all the way to -1. And then, actually that's a weird union symbol. It's a U. And then from -1 all the way to 2. and then 2 onward. Okay. All right, so let's keep trucking along. So now I need the limit as x goes to 2 of f of x. x2 is over here, so the limit as x goes to 2 looks like it's getting closer and closer to the same like kind of height of -1/2. So I'll just put -1/2. Next question. Same idea, limit as x goes to -3 of f of x. So yeah, this is a problem because as I go to -3, on the right side of -3, I'm getting a height like a little bit more than 1/2. But on the left side of -3, it's roughly, let's see, that looks like a little less than -1. But they're not the same from either side, so this is a does not exist. Okay, let's see the next problem. Okay, the limit as x goes to -1. So for this one, they're both going straight upward, so I would just put infinity. Okay, now for these next couple of problems, I'll actually let you do those ones on your own. That's just like plugging it in to see what height the function's at. So if you have any questions, feel free to post them to the discussion board. I'm going to start the last problem and then we'll take a quick break. So for number 3, find the value of c that will make the following piecewise defined function continuous over all the real numbers. So in order to like kind of understand this problem, I'm actually going to stop the video and start a new one in a different program. So I'll pause you right here and meet you in the next video.